Okay, this problem was actually posted on Wyzant several years ago, but I'm tutoring a student who's solving linear systems of linear equations using Gauss-Jordan elimination and also multiplying by the inverse of the coefficient matrix. So I thought I'd just answer this question to point that student to this video. This will be a little longer than normal, but here's the equations. X plus Y plus Z equals 12,000. That's the total investment return. This is the uh, annual return, total investment, I should say. The annual return is 815 based on these percentages of each investment. I decided to multiply every term by 1,000 to clear the decimals. And here's the fact that twice as much in bond B as in A. 2y equals z, so 2y minus z equals 0. So the matrix for A, the coefficient matrix, is 1, 1, 1, 45, 50, 90. That's from here. And 0, 2, negative 1 from this third equation. B is the matrix for these values right here. And what we're going to do for the technique that's suggested here is multiply both sides of this equation right here, where look at the black, A times the matrix XYZ equals B. Multiply both sides by A inverse. And here I make note of the fact that if you take A inverse times A, you get the identity matrix. That's why this side reduces to just XYZ. And A inverse, well, we'll talk about that in a second. How do you get A inverse? Look at that. But if you multiply it times B, you get these values. So there's the AAA, the AA, or actually the A and the B bonds. And here's an indication of how you might do that calculation. Matrix A inverse times B would take 46/19 times 12,000 plus negative 3/95 times 815,000 plus negative 8/19 times this 0. And you do the same thing for the second row times this column. So that works. Question is, if you had to get A inverse, oh, by the way, these black pictures are from a Desmos matrix calculator, which we'll talk about in a second. But how do you get A inverse, given that this is A? Well, I think probably the easiest way is using group operations. So here's matrix A on the left of that bar. To the right of that bar, we have the identity matrix where the diagonals are all 1, everything else is 0. And if we reduce row echelon form F, this becomes A inverse. That's probably the easiest way. How do you go about doing that? Well, you need 1 in the first column, first row. We already have that. Now if you now we want to turn zeros to all of these other elements, and there's a pattern to follow. I'm not going to go through it here, but you'll see it on the next board where we use Gauss-Jordan elimination. Okay, the other way to do it, which is quite a bit more complicated, is to get the adjoint of a 3x3 of the 3x3 matrix A by finding the transpose of the cofactor matrix of A. Well, what cofactor matrix of A, what is that? Well, if you want to picture, how do you get this element of the cofactor matrix. You picture crossing out that row and the column, and this is your remaining determinant. You evaluate that determinant, but you have to pay attention to the signs. So you know that if the row plus column number is even, you get a plus. If the row plus column is odd, you get a minus. So this is row 1, column 1. That adds up to even. So we're going to multiply with a plus sign this determinant right here. 50 times -1 is -50, minus 90 times 2, -230 is what goes here. And I won't go through the rest of those, but that's how you fill in all of the columns, all the elements of the D matrix, the cofactor matrix of D. The transpose of D is just interchanging every element on around the diagonal. So the 45 and the 3 are interchanged, the 90 and the 40, and the -2 and the -45. That's the transpose of the cofactor matrix. And now to get A inverse, you multiply that by the reciprocal of the determinant of A. And the determinant of A of a 3 by 3 matrix, there's a couple ways to do it. Expansion by cofactors is probably the easiest way, but you can also do this where you write these first 2 columns out to the right, and then you multiply the I'm not going to go through it. Gauss-Jordan elimination. Point you to a website that allows you to do the Gauss-Jordan elimination to solve a system of 3 or more linear equations. These are the steps. Here's the original system. Rewrite the system in matrix form. Notice that we add on the constants here to the right. And then the idea is to get zeros in all the elements and 1 along the diagonal. And you can take a look at what row operations are performed to make that happen. And if you divide 63,000 by 19, you'll get that number that we had for AAA bonds, A bonds, and B bonds. Okay, there you go. I'm going to post the answer to this and then post the link to the Desmos graphing matrix calculator and the Gauss elimination calculator. There you go.